Calculus video 41, related rates. So related rates is an idea where as one thing changes at a certain rate, it often affects something else, which then changes at a certain rate. That is the idea of two rates that are related to each other. So one example is this. If I have a circle, right? So consider a circle. Here's a circle drawn in black there, area pi r squared. It has a radius r. All right. And you're picturing that circle, the radius of that circle increasing, right? So it's one thing that is changing at a particular rate. You're picturing that the radius of the circle increasing. What happens is, as the radius of the circle increases, the area of the circle must also increase. Like you have the blue circle there, right? As the radius gets longer, the area of the circle increases. If you're looking at the rate at which that radius changes, if that's changing at a particular rate, then the area of the circle also will change at a particular rate. The rate at which the radius is changing is connected to the rate at which the area is changing. Those are related rates. Okay, so suppose the radius is increasing with a rate of 3 centimeters per second. So that's a constant rate, right? You're picturing the radius increasing at 3 centimeters per second. Every second it's 3 centimeters longer. The next second, 3 centimeters longer. It's a constant rate of increase. As the radius increases, the area of the circle also increases. Okay. However, in this case, the rate at which the area of the circle increases, the speed, right, at which the radius, that the area increases, it not only depends on the rate that the radius increases, it also depends on the current length of the radius. So I'm going to say that again. The rate at which the area of the circle increases depends on both the rate at which the radius increases and the current length of the radius. So let me see if I can make a picture that makes that helpful, at least make a little bit more sense here. So on the left here, we have a circle in black, right? So this circle drawn in black, that has a particular radius r. Let's picture the radius increasing in size, right? So that radius gets a little bit longer, and we now have a circle in red that's just kind of outside that circle, right? The circle is getting bigger. The circle and radius, the circle in red with radius red r is larger than the circle in black of black r, and the change in r is what we have there in blue. That sort of change in r. The idea I'm trying to get across here is that the rate at which the area changes depends both on the rate at which the radius changes and the length of the particular r at that time. So if we think about the smaller circle from black going to the red circle, the area changed by this much. This part in green is the change of the area, right? It was the area of the black circle. It's now the area of the red circle. And how much has changed is what I filled in there in green. Over a particular time would be the average rate at which that area changed. What I want to say is this. Let's take the circle on the right, the black circle on the right, definitely bigger than the original black circle we had, and we're increasing the radius again. But what I want to say is the amount that I've changed, the delta r, I want that to be the same. So the delta r on the left over there that I just drew, and the delta r on the right, going from black to red, is the same change in the radius. Okay, so you've got some change in the radius over time, some rate of change in the radius, some dr dt, rate of change of the radius. That is the same in both cases, right? That delta r is the same on the left as it is on the right. However, look at the area in green here. That's not green. The area in green, the amount that the area changed, even though the delta r is the same, even though the radius changed by the same amount, the amount that the area changed is quite a bit more on the right-hand side than it is on the left-hand side. And that's because the actual radius itself is larger. And so even though the radius in both cases are changing the same amount over the same amount of time, because the original radius was larger, the original circle was larger on the right-hand side, when it changed by that amount, you actually get more of an area, more change in the area. All right, so that's why we say up above that, starting right here, however, in this case, the rate at which the area of the circle increases depends on both the rate at which the radius increases and the current length of the radius. All right, the circle on the right, even though the radius changed by the same amount, got a larger increase in area because the radius itself started out as larger. How can we see this in like a formula? How can we understand this related rates idea in an equation? Go over here to, I'm originally have said the same thing. The rate of change in the area depends on both the rate of change of the radius and the length of the radius, kind of what I said above there. But let's take a look at this area formula. The area of a circle is equal to pi r squared. Notice A for area here equals pi r squared, r for radius. That this equation, A equals pi r squared, relates the area of the circle to the radius of the circle. That's what we need to use. So on the right here I have, note that we know dr dt. dr dt is the rate of change of the radius. Rate of change of the radius. dr dt. We know that. In the problem we were given above, if you don't remember, go way back up here, the radius is changing at 3 centimeters per second. That is dr dt. dr dt is the rate of change of the radius. We know that. We want to know what the rate of change of the area is. We know dr dt. We want to know dA dt. The dA dt is the rate of change of the area. So we have what we know, rate of change, dr dt. We want to know what is the rate of change in the area. That's the related rates. So what we have to do is we need to start with an equation that relates r and a. If we start with an equation that relates r and a, and then we take the derivative implicitly, when I take the derivative of the a, we'll get a dA dt. When I take the derivative of r, we'll get a dr dt. And that will allow us to relate the dr dt, the rate of change of the radius, with the dA dt, the rate of change of the area. So we take a look at the rates of change, and we want to relate with some equation the things we know, dr dt, with the things we want to know, dA dt. So we first start with an equation that simply relates r and a, radius and area, and then we take that derivative implicitly. Okay? So the formula A equals pi r squared is exactly what we want to use here, because it relates A, the area, with the radius r. So when I take the derivative implicitly with respect to t, a dA dt will show up and a dr dt will show up, and that's what I want. Okay, let's do an actual example, same kind of example here, a little bit more information. Suppose that the radius of a circle increases at a rate of 3 centimeters per second. So same thing we had above. And if you want to, go ahead and pause the video so you can write this problem down. All right, so suppose that the radius of a circle increases at a rate of 3 centimeters per second. What is the rate of change of the area of the circle when the radius is 4 centimeters? And that last part is important, right? Because the rate of change of the area will depend not just on the rate of change of the radius, 3 centimeters per second, but it'll also depend on the size of the circle at that time. That's what I was trying to show you with the two black circle, red circle, black circle, red circle. That the area, how much it changed, depend not just on how much the radius changed, but also on the size of the current circle. So here's what we know. Suppose that the radius of a circle increases at a rate of 3 centimeters per second. That means that the rate of change of the radius over time, dr dt, is equal to a positive 3 centimeters per second. Positive because the radius is increasing. If that had said decreasing, we would have done negative 3 centimeters per second. The rate would be getting negative, smaller. What is the rate of change of the area? So dA dt equals question mark. We want to know that when the radius is 4 centimeters. When the radius is 4 centimeters. Okay, so we want to know, well, we know dr dt, we want to know dA dt, so we're going to need to start with an equation, that relates r and a. Okay, we want to know dA dt. We do already know dr dt, so we're going to start with some equation with r and a in them. And that equation that we can use is the area of the circle is equal to pi times r squared. A couple of things to note here. Pi is a number. It's like 3 or 4. I mean, it's 3.14, but it's just a number, right? It's a coefficient. And so it's not a variable. We're not going to be doing the product rule on the right-hand side of the equal sign when we take the derivative. It's just a coefficient. Also, one of the biggest mistakes people make is they want to go ahead and they say, well, r is 4. Therefore, let's plug in 4. Therefore, my area is pi times 4 squared. That's 16 pi. And then they think, okay, let's take the derivative and see how the area is changing. And they take the derivative of both sides, and they get dA dt on the left-hand side because the derivative of a is dA dt. But 16 pi, that's a number, therefore we get 0 because the derivative of the number is 0. And this is wrong because the area is, in fact, changing over a circle when the radius is increasing. So the idea here is we don't plug in the fact that the radius is 4 centimeters at that particular time until after we take the derivative. So the note here will be only plug this into the equation after taking the derivative. Only plug the r equals 4 into the equation after taking the derivative. Don't do this right here. Okay, so let's start again. We have a is equal to pi r squared. What we want to do is take the derivative of both sides. Remember chain rule here. We're taking the derivative with respect to time. That's a dt down there. That means every variable that's not a t, we'll do the chain rule and multiply that by dA dt or dr dt, or if I had a different variable, that would times whatever variable that is, dt. In our case, we just have a and r are our only two variables. So when we take the derivative of a, we get 1 times dA dt, or just dA dt. Pi is just a number, so it's going to hang out here, times the derivative of r squared will bring the 2 down, r now to the first power, that's power rule, times, since that's an r, not a t, times dr dt, that is chain rule. Or, more simplified, we get dA dt is equal to 2 pi r dr dt, just rearranging the order there. All right, the thing we want to know dA dt. Want to know this. What is the rate of change of the area? Now we can plug in what the r is equal to, and we can plug in what the dr dt is equal to. We want to know what's the rate of change in the area when the radius is 4 and the rate at which the radius changes, dr dt, is 3. We can plug both of those in. We get dA dt is equal to 2 times pi times r, which is 4 centimeters, times dr dt, which is 3 centimeters per second. And if you do that, you get 24 pi. Now the units here it was 4 centimeters. It was 3 centimeters per second. So that's centimeters squared per second, which should make sense for area. Change of area is how much the area changes, centimeters squared per time per second. So we get 24 pi centimeters squared per second. Or if you want to multiply that out times the pi, you get about 75.4 centimeters per second. Sorry, centimeters squared per second. Right. So if the radius is increasing at a rate of 3 centimeters per second, when the radius is 4, At that moment in time, the area is increasing at 75.4 centimeters squared per second. Now, up at the top, I specified a couple of times that the change of the area, the rate at which the area changes, d/t, relies both on the rate at which the radius changes, dr/dt, and also the size of the radius. And we see that right there in the formula. In red there, the rate at which the area changes depends upon the size of the radius r and the rate at which the radius changes. The faster the radius changes, the larger dr/dt, the larger dA/dt will be. But also, the larger your r value, the larger your radius, the larger dA/dt will be. So the dA/dt depends on both r, the size of the radius, and also the rate at which the radius is changing. And we see that in the formula when we take the derivative implicitly. So that was kind of the intro into related rates and how two rates are related. The next couple of videos will be more examples of working related rates problems.